Now we have our last talk of the day.
Super happy to be involved. So thank you for having us. This is my first LUG conference, and I think Jinshan has been around for a while. Note that we do have a heavy focus on Lustre, so if you know folks who are interested in working on that with us, email me at cobbler@uber.com. So what is ATG and our mission? ATG is the Advanced Technologies Group within Uber. It's focused on self-driving. And why do we work on self-driving? Well, it saves lives. Around the world, 1.3 million people die in car accidents every year. The NHTSA in the US reports that 94% of those accidents are caused by human error. Self-driving cars don't get distracted. They're always attentive and focused on navigating the roads safely. It saves time. Fewer cars on the road reduces traffic, thus making your commute to and from locations faster. It saves space. There's over 1.5 billion cars in the world, and on average, they sit idle 94% of the time, which is just crazy. If we made better use of our vehicles, then we wouldn't need as many of them. You think about what we would do with all of that space if we eliminated a huge portion of the idle vehicles. Less parking garages and parking lanes, more green space, more bike lanes, things like that. It matters to Uber. At our core, Uber's been focused on improving transportation and making it more efficient and effective. We believe effortless transportation should be available to everyone in all the world's cities. And it matters to self-driving. Uber's network allows us the opportunity to scale self-driving technology, globally. So where are we? ATG operates in 4 sites currently, have about 1,500 engineers and operations staff. They work on board in San Francisco, Phoenix, Toronto, and Pittsburgh. It takes a massive effort of experts in a variety of areas to create self-driving technology. Our software team is focused on scaling a self-driving platform that functions in all of our core operating areas. Our mapping team is constantly generating real-world maps that form the foundation for the onboard software to use. The hardware team is focused on designing, iterating, integrating sensors and devices into our vehicles. And keep in mind that Uber doesn't make cars. We aren't in that business. So we need our vehicle programs team to build relationships with OEMs, tier 1 suppliers who can partner and help us produce vehicles. With all of the cars, we need an operations team to run our fleet, do real-world testing, get the information we need on actual experiences and situations that we design for. And in conjunction with real-world testing, our offline testing team runs millions and millions of miles. Sorry about that. Runs millions and millions of miles through simulated scenarios in our autonomy stack. So lastly, our safety team is there working with each group to ensure that we're improving and maintaining our safety standards as well. So we're going to use this driving situation and apply and kind of talk about how our autonomy stack sort of works in different areas. So this is a situation running on board one of the trucks that we have. And so we'll go through each part. So the cornerstone of the autonomy stack is the map. The map contains the prior information about our world. So using the map, we have a sense of what we expect to see in the world around us. This gives us the benefit of being able to know that this structure is a wall or a tree and not spend critical CPU resources on board trying to make that determination. I can filter out that information and focus on actors in the real world. So using the map, we need to figure out where the vehicle is in the world. And so localization is the process of taking sensor data and global inputs to determine the vehicle location in the local map frame. So now that we know where we are, we can continue using that prior data to pick our actors we see in the local area. So we use combined input from all of our sensor types, LiDAR, camera, and radar to fuse together a picture of where all the actors are. So once we've established what is being perceived, we need to apply behaviors to those actors. Pedestrians, bicycles, moving cars, parked cars, they all behave in different ways. So these behavioral attributes can be attributed to predict the trajectory of the vehicle. So now we need to plan our path, our own paths, to achieve our goals and set that trajectory. So you can see that we're predicting the car moving into our lane. We need to plan to slow down to keep our safe space. Our plan needs to send the right commands to the control system to apply the right values for throttle, brake, steering, and maintain that safe trajectory. So you'll see that in the control demo here. And all of that software integrated into the onboard hardware come together and are vigorously tested on a daily basis. So we develop our own test track to stress and challenge the self-driving technology in all kinds of situations. The course is designed with both typical and difficult to navigate road scenarios. And we have a kind of an overview picture of the track there as well. So now that you know a lot about ATG and what our software teams are kind of working on, Jinshan is going to come up and tell us more about how and why we use Lustre.
Hello? Is it working? Okay. Hello? Okay, thank you, Nick. So I'm going to talk about the software, especially, storage product we're using at ATG. Yeah, so we're building something really cool, changing the world. Okay, so I copied some slides, some words from an old slides, and I guess it should be written by some random dude at CMU, and it talked about some reason so why Lustre was chosen to store our data, right? So there are actually some investigation before because they are looking for an alternative solution to replace NAS. So the words are okay. So our traditional NAS was reaching its breaking point, and we have evaluated SEF, GlassFS, Lustre, and PNFS, but the Lustre was the best fit for our need, because of the following reasons. It provides POSIX semantics, so I guess this is a mistake because it should be POSIX API. As long as you are using single NAS, you don't care about POSIX semantics. And also it can achieve very high I/O bandwidth and hold well under heavy nodes. So yeah, right now it is still true that you have some requirements to the I/O bandwidth and performance. Lustre is still pretty much the only choice, even nowadays, right? So eventually, our jobs are spending more time on processing data instead of waiting for I/O. So basically, Lustre helped. Okay, so let me talk about the workload at Uber. So basically, at Uber, file sizes are variable. So they are, from different sources of data. So the first type of data is the logs are collected by self-driving vehicle. So as you can see from the video, so when the vehicle is driving on the road, and there's a lot of sensor like LiDAR, radar, and camera, they all collecting data. And those data will be imported into our data center and we're going to launch many jobs to analyze those data. So the good thing about the log is that, as long as it's imported into our data center, it won't be changed anymore. So another type of data is the executable binaries, because we use CI process, so things are moving really fast here. So before we release a new version of software, so we have to make sure it is good, right? So there's a lot of software release inside our data center, and they are basically very small files at the order of 10,000 binaries and executables. Usually several gigabytes in total size. So basically very small files. And also we have a lot of tiny files which are extracted from self-driving logs. And those files are basically images and small data file, and that are used as an input of machine learning jobs. So anyway, so the good thing is that the files are really complex, but the good thing is that all of them just write once and read it thereafter. Okay, so yeah, we have this complex workload and file types. We need a solution, right? But right now, Lustre doesn't support small I/O really well. So actually, we tried that before, and we just put small I/O and small file and big files into Lustre, and it didn't work well. Right now, people at ADG are kind of scared of Lustre. Yeah, it's quite funny. As a workaround solution, so we just store larger files into Lustre, and small files go to FreeNAS. So actually, this solution, especially for the large files, it works really well. Yeah, because Lustre can provide support of I/O bandwidth. However, the problem is about small files, because we store them into FreeNAS, and it has already become a bottleneck, for our job pipeline, because FreeNAS is good, it's very stable, but it is a single node, so you can't expect too much from it. So therefore, we are looking for solutions to migrate small files into Lustre as well. Okay, so the first thing popping into my mind is to use Lustre loop device, for the small files, right? So, just in case you don't know what loopback device is. So here, the pink guy is a Lustre loop device, and it uses a Lustre regular file, in the Lustre file system, and you can make local file system on top of it, and the interface between loop device and loop driver and the Lustre regular file is direct I/O. In that case, we can avoid double cache problem. So Lustre loop driver was removed from Lustre 2007 because there was a misunderstanding that Linux loop driver is able to provide the same functionality, but actually Linux loop driver can only support 512 bytes cycle size, which means it won't be able to do direct I/O to Lustre, because Lustre direct I/O has a limitation that it can only support page size. Based on this situation, I enhanced the original version of Lustre loop driver to make it be able to do async direct I/O. And this, it should be a very ideal solution for our workload because, as I said, so just write once and read mostly. So, I mean, the good thing about Lustre loop device is that it can convert IOPS problem into throughput problem, which is Lustre really good at, because it can avoid very expensive RPCs like open a file, you send an RPC to the MTT to open the file, and then you send another RPC to the OST to get the log, and then one more RPC to read the data, and then one more RPC to close the file. But with the Lustre loop device, you can just open the file from local file system like ext4 and XFS, so there's no overhead at all. Okay, so I enhanced the Lustre loop device and I benchmarked the performance. So actually, it turned out the performance is really good. Okay, so I just use test set as 50,000 files and 5 gigabytes in total, and I use different storage destination for my test case, right? Lustre directly and FreeNAS, and then Lustre loop with async I/O support, and original Lustre loop device, and Linux kernel loop device. So these different destinations, and I run OnSquashFS and sync for writing test, and MD5 sum for reading test. Just basically find all the regular files and then launch different number of jobs and do MD5 sum. So for the reader test. Okay, so as you can see, so these are the OnSquashFS for the writer test, and this guy. Okay, so I just measure the number of seconds to finish the work. So basically, shorter is the better. And you can see the gray bar. That is my new Lustre loop device with async support. It's almost the best in all of the tests. So this on Squash. So this MD5 sum with 1 job, 4 job, 8 job, and 16 jobs. So the gray bar is new Lustre loop driver. So yeah, it's pretty good. Okay, so from Uber's perspective, in order to enable AI workload on Lustre, so I think we're going to need those features. Of course, different facilities may have different requirements, but I just only speak for Uber. Okay, so data on MTT, that is the most important thing for us because we have so many small files. Yeah, but unfortunately, so we have to wait for a second phase to take full advantage of data on MTT. So another feature actually, turns out to be useful is that is file level redundancy. Yeah, because anyways, because it will increase read bandwidth, dramatically. Because so if we had FLR, we could distribute workload, read workload across multiple OSTs, and therefore we can address the problems like 3,000 compute nodes need to read some file from shared storage to get started, right? So as long as you have many OSTs, so basically you have many reading bandwidth. Also, it could be useful, if we have something like compound RPC. So basically, when small files are being accessed, it is going to produce a lot of small RPCs. So right now, each RPCs are sent to MDT or OSTs individually. So this is not good. So if we can make a compound RPC, just merge those small RPCs into a big RPC and send them as a single RPC to the target. So the performance would be really good. So for example, there are some low-hanging fruit for the compound RPC. Like, so right now when we read a file, we have to open the file and send read RPC and then close it. Especially on the close phase, we are doing it synchronously. So we have to send the RPC to the MDT and then get result back. So this is not necessary. So for example, we can do async close. We can just, okay, so when one client closes a file, it just put a request on some list at MTC layer. And then, at a later time, when you have a bunch of closed RPC sitting there, you can just pack a compound RPC and send the closed RPC, compound closed RPC to the MDT. Another very useful case is for the get RPC, right? So basically, very useful to apply. There's almost no risk as far as I can see. But we don't care about that. Okay, yeah, that's it.
Just for the record, you couldn't actually send close RPCs like what you've described because that will break the other openers. You could only safely do this for files you opened for reads, but if you open a file for write and then you hold on to this close RPCs, then if another guy comes in and tries to execute the file, they'll get an error. So, I mean, you need to be careful about this. And there is a reason we have those open locks because we do need notifications when things are happening. So
yeah, that's true. So of course, there are a lot of exceptions, right? So like, you have close intent, you can do that as well, right? So, but most likely you can do a lot of things like, okay, so there's a recent bug about executable plus open lock. So basically, we can fix it on the client side as well. So basically, if your file has executable bit, and you shouldn't cache open lock or close or async close RPC at all. Yeah.
So the thing is, everything's possible. I mean, just don't think everything's like super easy, and if you batch things up, you save time. You actually need to be careful about all of that stuff.
Right. Yeah.
Can you go back 2 slides, if I'm not mistaken? No, just one forward, sorry. The other direction.
One more?
No, towards the end. One more. Yep, that one. So address the problem of 3,000 nodes to access the same file at the same time. I mean, yes, file level redundancy will probably help, but while waiting for that, there are other options like one node reading the file and then multicasting or broadcasting it to the other nodes if your network bandwidth is sufficient enough. So
yeah, that will work. Actually, I have already made some proposal. Like, yes, okay, so we do have, last loop device, and we can use a regular file as a local file system, right? So actually, we can do this into our job pipeline, like, add 2 new phases, like a pre-stage phase, just copy files over multiple OST, and then do a job, and there will be a cleanup phase, just delete all of those duplicates. Yeah, it's good, yeah.
This is a comment to let people know. The Lustre loop device will not come back. That will not come back. So this was asked before at one time when we removed it. The reason at that time is it was pretty much on par for performance and things like that. So, and the upstream guys did not like that. And if we do any enhancements like that, that needs to be addressed in the proper loopback driver. Because
Well, yeah, that will take time. But actually, I mean, yeah, I saw the ticket. You know, it has reasons to move.
yeah.
To
Well, we
back to Vice. Yeah, I saw it. Yeah.
yeah. So it would be kudos because it earns us points with the upstream guys to fix these kind of things. The other thing is that I know you posted the patches and you send them to me and Neil, but what was missing, what wasn't very clear, we need exact reproducers to see where these problems are in the default loopback driver.
Because you can just, you know, download download the latest loopback device utility, and you can just turn direct I/O, and it immediately bang, crashed.
Okay, so it's just the direct I/O and the sector sizes. Those are the issues.
You want more? So actually, you know, there's a limitation.
No, it's good. Yes, I do want more because I want to be able to address these issues and fix them upstream.
Yeah, I mean, yeah, it would be great if we can make this work into Linux kernel, and I think Neil Brown is a very good guy, you know, to do this work. Actually, I can make some good patch and send it to him, and maybe he can take it over, you know, to get it merged. Yeah.
All right, so it's just direct I/O. That's if I just turn it on that and
no, there's
run it.
more actually.
There's
Anyway,
more.
Yeah.
All right.
Okay, one more question. Anyone?
It's some kernel that support direct I/O, support loop device direct I/O 4.4 or something like that. Yeah. Actually, you know, any kernel you can see the problem.
Wait, well, let's take our speaker.